now going to look at a particular type of first-order differential equation called a separable equation. So we'll start with the first-order differential equation, which is of the form dy dx equal to f of xy, some function involving x and y. And the idea is we want to be able to rewrite this in the form dy dx equal to g of x p of y. So I want to be able to write this function on the right-hand side as something involving only x's times something involving only y's. And ultimately what I really want is to be able to write it as h of y dy equal to g of x dx, where h of y is 1 over p of y. So let's start with looking at a couple of differential equations and seeing if they are actually separable. The first one I want to consider is dy dx equal to 2x plus xy over y squared plus 1. So let's start with the numerator and let's factor it. We can see they have an x in common, so let's factor out the x. I then have dy dx is equal to x times 2 plus y over y squared plus 1. So we can see that the x involves only x's and then the fraction involves only y's. So we have that g of x is equal to x and p of y is 2 plus y over y squared plus 1. So this is a separable differential equation. Let's look at one more. The next one I want to look at is dy over dx equal to 1 plus xy. And this time there's no way to factor that right-hand side so that I have a function with only x times a function with only y. The 1 is going to mess that up. So this one would be not separable. So now that we've talked a little bit about what separable means, let's look at how to solve them. We know we have a separable differential equation, so we know it can be written in the form dy dx equal to g of x p of y. And I'm going to let h of y be equal to 1 over p of y. So if I multiply both sides by h of y, I get h of y times dy dx is equal to g of x. I'm also going to multiply both sides by dx. So I now have h of y dy is equal to g of x dx. The next step is going to be to integrate both sides. So I have the integral of h of y dy is equal to the integral of g of x dx. And from this we can get the solution. I'm going to let a capital H and a capital G denote the antiderivatives of h and g. So I have capital H of y is equal to capital G of x plus c, where c is my constant of integration. So let's do some examples. So I have dy dx is equal to x minus 5 over y squared. We can multiply through by y squared dx. That gives us y squared dy is equal to x minus 5 dx. The next step would be to integrate both sides. We know the integral of y squared is 1/3 y cubed. The integral of x is 1/2 x squared. The integral of negative 5 is negative 5x. And then we need our constant of integration. So I now have an implicit solution, 1/3 y cubed equal to 1/2 x squared minus 5x plus c. The next problem, dy dx equal to 6x to the 5th minus 2x plus 1 over cosine y plus e to the y. Multiplying both sides by cosine y plus e to the y dx. That gives me cosine y plus e to the y times dy equal to 6x to the 5th minus 2x plus 1 dx. We can then integrate both sides. We know that the integral of cosine is sine. The integral of e to the y is e to the y. The integral of 6x to the 5th is x to the 6th. The integral of negative 2x is negative x squared. The integral of 1 is x. And then we need to add our constant of integration. So I now have an implicit solution of sine of y plus e to the y equal to x to the 6th minus x squared plus x plus c. Let's look at one more. The next problem is an initial value problem. We have dy dx equal to y minus 1 over x plus 3, and we know y of negative 1 is equal to 0. We multiply both sides by dx over y minus 1. That gives us 1 over y minus 1 dy equal to 1 over x plus 3 dx. We then integrate both sides. We know the integral of 1 over y minus 1 is ln of y minus 1. And we know that the integral of 1 over x plus 3 is ln of x plus 3. And then we need our constant of integration plus c. We also do have an initial condition. We know that when x is equal to negative 1, y is equal to 0. So I can stick that into this problem. So I have ln of absolute value of negative 1 is equal to ln of 2 plus c. We know that ln of 1 is 0. So I have 0 is equal to ln of 2 plus c. Therefore, I have negative ln of 2 is equal to c. So I have my solution. Ln of absolute value of y minus 1 is equal to ln of absolute value of x plus 3 minus ln of 2. And we can absolutely use properties of logarithms to combine this and simplify this answer as well.